My name is Muhammad Afiq Ezek, and I am doing the introduction part for this project. First is water level is a valuable natural resource that is used in a variety of industry, chemical, commercial, and agriculture operation in addition to sustaining life. For example, water pump that is used in agriculture area in order to give regular water to plantation or farm ground. Second thing is the water level must be kept at the desired set point. By doing this, you need to integrating the system in a feedback control system. A controlling system such as proportional, integral, and directive (PID) controller plays a vital part in maintaining the precise level. The third one is to boost process productivity and safe usage of water by maintaining the required water set level, but it is also to help save water by monitoring the level and eliminating overflowing water in the storage system. Last but not least, the goal of this project is to incorporate real-time prediction control algorithm into tank for level control operation using PID controller. That is by evaluate the control performance using MATLAB simulation with the same controller, which is Simulink. Okay, that's it for me. Now I'm going to pass it to the next presenter.
Thank you to the previous presenter. My name is Nurul Afifa Binti Alias, and now it is my turn to continue the presentation for my part, which is the state of the art. In the state of the art, there are four parts, which are the type of controller used, the transfer function of the plan used, the optimization method used, and the advantage and disadvantage. So now I will proceed with the type of the controller used. In our mini project, which is water level controlling system, we are using the water level sensor and PID controller. It can fine-tune the controller's responsiveness by altering three sorts of multipliers. There is professional component QP, which is the main drive in the control loop to reduce a large portion of the overall error. Next, an integral component KI. It is to reduce the system final error. And last, the derivative component KD, which is to help remove overshoot but has little effect on the overall error. For an example, the engineers use a mathematical model of the system to design a controller based on a linearized model of real control system in the past. Next, the transfer function of the plan used. The combined response of the forward pass and the feedback loop is the overall system response. Let G represent the relationship between H and W as the SDH system impulse response. By combining all of them, it may get an expression for G, which is the Laplace transform of G. When they are added together, W is connected to H as the follows. This is the equation that I had explained just now. Next, in the Laplace domain, the relationship is like this equation. And then, as a result, this is the equation that shows the transfer function of G. Lastly, the forward pass total transfer function F that can be calculated by combining the transfer function. So this is the equation shown. After that, the optimization method used. PID controller was a combined control system of proportional, integral, and derivative control by considering all the performance of each output. In this method, the adjustment was done in a closed loop, where the reference input is used as a step function designed in the system. This method sets the parameters Kp, Ki, and Kd so that it was obtained after the system output was reached in the state of steady state. And last, for my slide is the advantage and disadvantage. For the advantage, with automatic controllers, electricity consumption is limited and less water is required to regulate supply. It also saves money by reducing water and electricity waste. And this system is that they self-regulate. For the disadvantage, the maintenance must be performed on a regular basis to ensure that the system functions properly. Next, the wildfire is a problem caused by a lack of short-circuit protection in the water level control. And lastly, it can be rust, cool, and degrade. That's all from me. Thank you.
Hello, my name is Muhammad Azim bin Muhammad Azali. I will explain the methodology of this project. In this methodology contain two parts, which is system model and modeling for motor pump and PID control. Okay, first of all, let's see our project water level diagram. As you can see at here, it contains three parts. The first is DC motor, PID controller, and storage system. And how this project works? Okay, the motor pumps water to the container at a rate of Q in, which is as here, through an inlet pipe. The container with cross-sectional area A is filled to water level. Water level is H, and water is leaving the container at a rate of QO through an outlet pipe, which is located at here. Next, let's see this project, this system block diagram. As we can see, at the input is H0, and then it go to the first block, which is PID controller, next to the motor pump, then STH. Okay, next how this block diagram works. Okay, the overall system is a feedback control system. The H0 is to show the specific level the tanks need to be filled, while the PID controller that control the speed of the DC motor. The speed of motor is going to be transformed by STH, which represent by speed to high transformations block that relate the speed to the rate, so that the water level HT. After that, the water level HT and this information is feedback at the input. As we can see here, after it goes through the STH, it feedback to the early of the system. It will feedback at the input and compare with the reference desired level. The ET or we can call it error are going to be a signal to the PID control Therefore, it's going to adjust the speed of the water, either is increase or decrease, depend of the level of water level, to regulate the rate until the specified target water level is achieved. This is the mathematical modeling for motor pump. This is the motor pump formula, which is J is represent of moment of inertia of the motor, P is a motor viscous friction, KE electromotive force constant, KT motor tongue constant, R is electric resistance, L is electric inductance. This is the equations, and this is equation after transfer functions. This is for the motor pump, and this is the transfer function for in PID controller, which is CS equal to V over E is equal to KP plus K2 over S plus SKD. Okay.
My name is Muhammad Ridwan bin Muhammad Hanafi, and I will explain about the result part for this assignment. The first figure is for the structure of PID controller. The input is given from a signal, and the signal will be transferred from the 3 points, which is the KP, KI, and KD. The KP is proportional gain, the KI is integral gain, and KD is derivative gain. The derivative gain require derivative block because it is used to derive the value that is signal from the source. The KI require the integral block because it is to integrate the input to change the input based on the requirement, and the three input will be combined in the transfer function. For the next figure is the water tank with PID controller. From the three input, which is the KI, KD, and KP, will be put in the PID controller and signal to the output, which can be seen at the scope. This is the value that is obtained from the water tank. Then we use the PID tuner to tune the system to obtain zero shoot and small settling time. The PID tuner also allow us to tune the signal to obtain the required output. The parameter for the P, I, D, and N is measured. As you can see, the performance and the robustness for the step plot is stable, and the overshoot is below 5%, which means that the the flow has no problem occur. That's all from me. Thank you.
Hi, my name is Muhammad Hazim bin Jawri. So I would like to discuss about the result that we get by changing the proportional integral and derivative parameter. We can see the effect of increasing parameter. You can see the effect of the changing the parameter in the table. For parameter KP, the rise time will be decreased, overshoot will be increased, settling time small change, and steady state error will be decreased. For KI, the rise time will be decreased also, overshoot will be increased, settling time will be increased, and steady state error will be eliminated. And for the KD, the rise time will be small change, overshoot will be decreased, settling time will be decreased, and steady state error will be none. Effect of changing PID function. For P, the pros is easy to implement, but the downside of it is long settling time and steady state error. For PD, the pros is easy to stabilize and faster response than just P controller, but the cons is can amplify higher frequency noise. For PI is the pros is no steady state error, and the con is narrower range of stability. The most common controller used in the HVAC industry is the proportional integral derivative PID controller. In brief, proportional integral derivative PID controller is a feedback controller that helps to gain a set point regardless of disturbance or any variation in characteristic of the plan of any form. The proportional gain simply multiply the error by a factor Kp. The integral terms is a multiplication of the integral gain and the sum of the recent error. The integral terms help in getting rid of the steady state error and cause the system to catch up with the desired set point. The derivative controller determine the direction to the rate of which the error has been changing. In most of the HVAC system, it is not necessary to use the derivative part of the PID. Hence, in this project, only PI controller has been designed and used. There are a couple of strategies on how PID can be tuned. These include trial and error tuning method, Ziegler-Nichols tuning method. Our method was calculating the controller output function U such that the final output signal applied to the actuating circuit was divided by the number of the shift determined in PID structure. To improve on the effect of Kp, an additional Ki was also set to a small value. Adding integral gain had a great effect on reducing steady state error between the desired temperature and the actual temperature. Multi-single input signal output SISO PIDE loops. After establishing a functioning single input, single output PID, a PI control which was the simplest in design since we use data from one sensor to control one actuator. We moved to designing a single input, multiple output SIMO PI control. After establishing a working SIMO control, we decided to implement two decoupled PI loops known as MIMO control, controlling the temperature of the chiller water loops, and the second PI control loop was to manage the temperature of the air supply S by controlling the chill side pump. The slower the rate, the longer the water stays within the cooling coil. The warmer the CHWR, return temperature gets.